Okay. Just like to thank my team for nominating me to talk again. It's very kind of you. So to refresh your memories, we were looking at how we could improve the model representation of collection networks. So the current state of affairs is that manholes collect and issue floodwater, and often the manhole's location is determined by GIS information, so they're not in an ideal location, certainly for collecting water. Hence, the 2D domain of the flooding model ends up with pooling artificially, which in reality should enter the sewer network, head downstream and possibly cause more flooding, or at least a flooding event of a longer duration. So I suggested in my talk a few days ago some potential solutions. Direct representation, that was binned by the group. An automated build based on design guidance, also binned by the group. And this was my best idea, a lumped model or collection subcatchments that took a sort of uniform amount over a geographically predetermined area. And that was binned by the group. So even before we got into the room, someone else had a better idea. Thanks, Gavin. Line sinks, it doesn't require nearly as much GIS effort. You can simply take the road polygon shape and shrink it, and you can create these line sinks quite easily. So it has the best benefit to sort of effort ratio, if you like. So when we got in the room, our initial approach was that we would model the 1D surface water equations for the network. We would model the 2D shallow water equations for the 2D model. We couple the two models at manholes and gullies. And then our test case would be to remove the gullies and replace with line sinks to see if we could tune the line sinks to match the performance of the gullies. So this resulted in miserable failure. It's far too hard to create the two models and couple them in a few days. So I'm going to get someone else. Chinadu, do you think you could talk about the shallow water equations?
Yeah.
Would you like to come up and talk about it? So I'm not really qualified to describe these to you, so I get my colleague here to have a go.
So you have it here as well?
Yes, it's on the next page.
Okay, this is the 1D equation. So this is the equation we use for the channel. Is it working? Yep. Okay. So this is the equation for the channel. So ideally, what we were supposed to do was to use this equation to model the dynamics of the flow in the underground channel, that's the pipe, and then use this one for the flood model, that's the 2D, the surface for the surface flow, and then couple the two. But what actually happened was that we already have a code for this model, and we also have a code for channel model, but the channel model code we have is for open channel, not for closed pipe, because the problem we have here is a closed pipe. So we tried to test this, our code worked, our 2D code worked. So when we tried to test the 1D model, it also worked for open channel, which is what it's meant for, but it didn't work for the closed channel, because that's not what it's meant for. And then when we look at the problem, because we understand that what is done in the software which they use, the tool they use, is actually they do some artificial thing on top of that 1D model, 1D code, which after we considered the whole thing, we saw that it was not possible to do it in 1 or 2 days. So based on that, we saw that it was difficult for us to get the underground model working properly for us to couple the two. So we decided that we are going to consider the underground as a sink only. So we study the flow on the surface and then model the coupling of it, that's the sinking of it through the manholes and the gullies into the underground. So that's actually what we did. So we focus on solving the free surface equation to the flood model, and then couple it, solve for the sink into the underground. So, and then study the effect of how it goes underground using the gullies and the manholes. So you can continue.
Okay, thank you. So these are the coupling terms that we were going to use in our initial approach to exchange water between the surface and the surface 2D model and the 1D network model, if you like. So we considered 3 scenarios where we had free discharge to the network, had submerged discharge to the network, and then we had the network flooding. But in the end we decided that we really didn't have time to couple the 2 models. So as Chinadu said, we revised our approach. We binned the 1D model and we focused on scenario 1 where there was capacity in the underground network to receive flow from the surface, and that allowed us to represent the manholes and gullies as simple sinks in the 2D. And that water never returned to the model, but it was probably sufficient for our purposes. And the other sort of strategic change at this point was to pursue 2 2D models. So we pursued the shallow water equations and the diffusive wave equations. Our test case remained the same. So this resulted in success because we didn't have to do any coupling, which was difficult, and we didn't have to get the 1D model working. These are the diffusive wave approximation equations, and I wonder if, Gavin, you wouldn't mind explaining them?
Okay, so this is an approximation that's used in lots of operational flood models, and it's based on the idea that when the flow, when a flood is often friction dominated, and the inertial terms and the momentum equations turn out to be not too important. And when you make that approximation, if you make a balance between the pressure gradient terms and the friction terms in the momentum equation, you get you work out an expression for the velocity of the flow as a function of the slope of the free surface, which is this gradient of h times b. B here is the bottom topography, and h is the layer thickness, and the layer thickness itself. And this formula is called Manning's formula. And the result of that is that you then have a kind of nonlinear diffusion equation when you put this u into the mass conservation equation. You end up with a kind of nonlinear diffusion equation, and the things on the right hand side of this equation here are R is a source due to rain, and then the other thing is a sink due to our manholes and drains, which are located at the points xi somewhere on our river. So shall I hand it back at this point, or is there, what happens next?
Yeah, forgive me.
Oh yeah, okay. So this is then a schematic of the setup that we were as we described it. We have a parabolic road which represents the camber of the road, and a pavement at the sides, and in common with Grange Road over there, we put manholes in the centre of the road every now and again, every 30 metres or so, and drains at the side of the road every 10 metres or so. And then we discretize the road into square boxes, as you can see on the picture. So,
You can just keep going if you want, but...
well,
I don't want
maybe, yeah. So I don't know about these results. So maybe you
Okay,
can have
all
a go.
Thanks, Kevin.
we like the improvised.
Okay, so this is what we have in the model I use day to day, just manholes. So this is a 2D simulation we ran. We actually probably dumped too much rain into the 2D domain, so it doesn't tell you a great deal. But you can see that the manhole is acting as a sink. That's about as much as that tells you. We then added the gullies as sinks into the 2D domain and removed the manholes. So there you go. Obviously the Z coordinate has been exaggerated somewhat. And then the sort of third scenario was the line sinks, and you can see that the line sinks there. A very similar video of the water receding into the line sinks.
James, it might be useful to note, so the scaling of all of those results are basically blown up by a factor of 20 so that you could actually see what was going on. So it's not that much water was thrown in.
Yeah.
It was just so you could actually visualize what was
Yeah.
happening.
But our initial run, you can see that the percentage lost through the sinks between having 10 gullies, 100 gullies, which is effectively a line sink, and 3 manholes, very similar. And that is because the whole 2D domain was completely inundated, so the benefit of having the gullies was removed. So we brought down the amount of water dumped on the 2D domain such that the camber of the road became sort of effective at directing water to the gullies, so it's a bit more of a realistic picture. And there we saw that 10 gullies, so that's like a direct representation of the gullies, gave us 9.5% lost from the water deposited. The 100 gullies, which is effectively our line sink, gave us a very similar amount of fluid lost from the 2D domain. Whereas the three manholes, and this is the result we wanted to see, collect far less water because they weren't in the right topographic location to do the job. So that's good. It turned out that both our approaches, both our modelling approaches were successful. So this is Gavin's model, the diffusive wave equations, and I believe this is water depth down the longitudinal axis in the centre of the road. Is that
It's averaged across.
averaged across the road?
It's the layer thickness averaged across the channel.
Okay.
30 centimeters to begin with.
Okay. So the dotted line is time 0, and the continuous line is after
30 seconds or so.
30 seconds. Do you want to talk about these? This is the first time I've seen them.
Yes. So what can be said about this? Well, so this is the flow. We're solving the sort of nonlinear diffusion equation, which you get from the balance in with Manning friction, and the flow is driven by a slope in the road. So the idea is that our road here is 100 meters long, and it drops by 2 meters over the length. So it's that gradient in the road that's driving the flow. And so I start with a Gaussian blob, which is about 20 meters across and 30 centimeters deep, and the model is run for a real time of 30 seconds, and you can see that unsurprisingly the water flows down the road. So at least the model is doing roughly the right thing. Do we believe the numbers? Oh, I hope so. So now we're in a position to add in. So this is the solution one where we just have a road. So we can now start adding in some sinks into the problem. And so this is with 3 manholes in the centre of the road. our domain here is periodic in the x direction, so the flow can continue up. So you can almost think of this as an infinite domain with lots of initial blobs on it, and this flow will continue out the right-hand side. And so here there are 3 manholes, and the effect on the flow, unsurprisingly, is that some water goes down these 2 manholes here, hasn't reached the 3rd one, and there's some loss of fluid overall, which you can see on the plot. What have we also added in gullies? So these are gullies at the side of the road. There's a camber in the road. There are gullies every 10 meters, and so here you can see loss of. On this picture, you can see loss of the water into the gullies, and you can see that there's actually considerably more water lost down the gullies than there is down the manholes. There's a reason for that, and that's because if the road had been flat, only 2/3 as much water would go down the gullies as down the manholes in the problem, because that's the way I've set things up. But what's happening is that the water is deeper at the sides of the road, or the layer is deeper at the sides of the road, so more water goes down the gullies because the formula for the open weir sink, the sink is proportional to the depth to the power of 3 over 2. So where the flow is deeper, the sinks are more efficient. So then the question that we wanted to pose to go some way to start to answer James's question, what's the best way of representing these in a more complicated model, is supposing we take out these gullies and replace them with a line sink with an equivalent sink associated with it. Well, that's ignoring throwing away all the information about the location of the gullies and just parameterizing them effectively. Well, do you get the same result? And it turns out that you do more or less. The green curve is the situation with the line sink. You can see that you no longer see the locations of the gullies in this plot, but you get the exact same answer more or less for the flood when you parameterize the line sink. So that shows that at least as far as the gullies acting as a sink are concerned, when you put the real numbers in, it's pretty reasonable to replace them with a line sink. Okay, do you want to hand back to
That's the next stuff, so.
right?
Oh.
Right. Okay. Right.
Do we finish?
Yes,
with
that's
that?
it.
We're going to sum up.
I mean, I have a question.
We've stunned them.
I have one, maybe.
Good.
There's a question for Gavin. This formula for the how much water is flowing through a hole. I mean, how is it obtained? What kind of approximation?
It's it is a sort of standard formula in the engineering literature for an open weir, like a hole. A hole under flow. So it's the formula for the flow over a weir into a hole, I suppose. And so there are various terms that appear in the full formula, where the weir perimeter is one of the key parts to that.
But it's obtained by some reasonable approximation.
Yeah. So it's the hydraulics of it's from considering the hydraulics of a weir. Maybe you know more about this actually.
I think there's a few different weir equations. They're probably based on the water surface passing through its critical depth over the crest of the weir, and they work away from that.
Hydraulics.
Yeah, hydraulics.
Albert can explain it better.
Albert could give us a better explanation.
I think that adapting this, right. I think they're doing quite well, and adapting this equation is general we're using in hydraulic modeling to represent this. It's kind of empirical already also been verified by experiments. So quite general equation. How we try to evaluate. We also seen the previous one in the leaky dam example. They are using similar equation to determine how water flow over the dam or through the gap between the dam. Yeah, but I'm quite impressed by what you've done. This is very interesting to identify this need to further investigate the gullies, how they will contribute to the flood modeling. And I'm also appreciate that you say that it's difficult to couple 1D, 2D model.
It's very difficult.
I know it's not some proper education for us.
That proved my PhD thesis is
Are further questions, David?
So, can I ask you whether you think that the results are as you expected? I mean, I'm slightly surprised that the overall effect of adding in all these gullies and drains, etc., is really just to reduce the wave propagating down. It doesn't really have any major global effects other than that.
Just the amount of water. What else do you expect it to do?
Well, so the moral is that you can put them anywhere, and you just know by how much you're taking out through the total number of gullies that you're going to diminish the wave, etc. I would have thought that you might have expected something more than that.
No, that's a good result for me. Currently in the models, the gullies aren't represented at all, so we don't have an effective way of collecting water from the 2D and depositing it in the 1D. So direct representation of all the gullies would be computationally and resource intensive. So we were looking for an approximate method which would give us the same performance, and actually we were able to produce almost exactly the same result with a very approximate method, which will save a lot of human effort and computational effort. So I was quite happy actually.
Yeah, no.
So you showed the comparison between what I think was a direct representation and then the approximation at the end, and the curves fit on top of each other. Can you comment on the cost of the two methods? Was the line sync particularly less computationally intensive than that direct representation?
Well, in the model as I coded it up, the sinks were pretty much free computationally. It was solving the diffusion equation was the
So I couldn't work out if your line sync was in fact loads of gullies. In fact,
it was, yeah. So
Sorry.
it's one gully per element. Where
okay. So potentially then that's quite a difficult thing to sort of scale up into how that could be implemented in the real model.
No, because the sinks aren't a significant part of the computational cost as implemented as we're suggesting they should be implemented.
So I have a question which follows on that. Just a short one. You could also use the shallow water equations instead of the diffusion equation. Could you comment on using either one? But then the second question, which is more pressing, was I thought that was in the original challenge. James told us that they don't quite know where the sinks are because they don't have the plan. So so now you can model the sinks as line sinks or point sinks. How would you be able to infer? Well, with the line sinks has the advantage that you don't have to precisely tell where they are. But the question is how do you know what the strength is? Because that's the big question in reality. Have you thought? Well, you couldn't do that this week, but have you thought how you would address that? Because that's in some sense the real problem. What is the actual sink strength? Correct. That's what I gathered from your presentation on Monday.
Sorry, what was the first question?
But the first question was a simple one: comparison between shallow water and the diffusive approximation. So that's probably for Gavin.
Right, so unfortunately we didn't really have time to coordinate our shallow water modelling effort with the diffusion one, so it would have been nice to have solved exactly the same problem in both and to see what difference it made.
Yes.
But I think generally speaking the diffusive wave suffers from having velocities and things a bit too high if the scale of the if there's a lot of variability in the free surface height, for example. I think it spreads things out a bit too quickly. So that's the.
Okay, but then the burning question was for the group, for James, is how would you tackle figuring out the strength of the sinks? That's the difficult issue.
The strength of the sinks.
Yeah, how do you know?
So we've tried to. So we had a simulation where we had the individual gullies as sinks, and then we matched our line sink to that volume. So we've tuned our sort of solution, our line sink, to the individual gullies. So that was the goal. Does that answer the question?
And no, how do you know? how do you know in a real city, in a real case, what the strength is of your sinks?
So
Because
in the real city, we know exactly where the manholes are and how many, and for each manhole there's going to be, say, 10 gullies in real length.
okay,
And so we can now approximate these gullies
by line
around the actual location of the manhole that we know, but at the side of the road instead, which is an improvement on the current model.
Okay.
Thank you.
Very good. So this
Okay.
Albert, very.
Thank you. I just want to add a comment to previous comment. I think what they're doing is try to identify how this gully contribute to the flood reduction on the surface for some locations. But if we couple this with the sewer network model, that will, because more water going to the sewer network, they will shift the flood risk to somewhere else. That we might need some further investigation for this, and also since that the surface water been reduced for some areas, so they might have different strategy for coping with the flooding.
Can I make a comment?
Oh.
Okay. In addition to your question, if you look at the first result, the videos he showed, those videos are done with shallow water equations. So we solved shallow water equations. That's the code we had already. So, and he solved the diffusion equation. So in the shallow water equation results, you saw when he was showing some tables. So we calculated, with respect to the intensity you're asking of, we calculated the amount of the mass of water that is being lost through the gullies. So we compared it when we have line sink and point sink. That's what you're seeing when he showed 99.something% and 10.something%. So to your two questions about the equations, we saw both shallow water equations and diffusion equation. And in terms of intensity, we did that through calculating the mass of water that is lost based on the arrangement. Thank you.
Very good. Let's thank the group for their